And there we go. So welcome everyone to our IFERC GPU workshop in December 2020. We are really happy to have this workshop, and thank you to all of our speakers to giving the upcoming talks. And the first talk is given by Richard Kamenje. So Richard, please go ahead.
So can you hear me all?
Yeah.
Yeah. So good morning, everyone. It's my pleasure to welcome you as well at this event, this workshop that we organize within the context of the IFERC. You probably are aware of what IFERC is. I suggest that I don't spend more time talking about IFERC. Just to say maybe that our collaboration on HPC between Japan and the EU goes back to the time of Helios, where we had a fantastic supercomputer jointly implemented in Rokasho. So this has prompted us to keep continuing the collaboration, exchanging on technical information, scientific information, and today even exchanging computing time on both sides, trying to foster the advance of fusion computations in support of ITER on the one hand side, and also in support of demo. And I think this is a very nice endeavor. And it is within that spirit that we discussed about organizing this event, the GPU workshop, in order to share on both sides of the, I would say, ocean, the Pacific, to share our understanding on how to make best use of GPUs for fusion applications. As you know, GPUs are coming for us in particular, and we are still struggling in trying to adapt our codes to this architecture. So the idea is to try to make the best out of what the market offers, and this seems to be a very important play on the market today. And my hope is that at the end of the workshop, we on the both sides will have a better understanding of how we each other make use of this GPU and how we each other can help ourselves to even increase this understanding of how to use GPUs. So we, at least within Europe, have been trying to boost, in some sense, the usage of GPUs, offering to our users a number of elements that could help them to better understand the architecture, better make use of it for fusion applications, given the various algorithms that we use. And I have to say the success so far has not been that great. We, in some sense, understand that people are really struggling to make use of that. We see that in particular with the usage of the resources that we have. As you probably know, in the EU, we have the Marconi Fusion supercomputer that is based in Italy at the Cineca site in Bologna. And in there, we have a significant fraction of the resources that is in this GPU architecture. And the usage so far has not been convincing, actually far from it. And what we hope is that we, by providing support to the users, by better understanding how to make use of this, how this architecture is in a way organized, how we adapt our codes to this architecture, that would make better use of these resources and take advantage of what this architecture brings. We know of them, but we still have to understand how we take advantage of that in our own computing environment. So yes, we look forward to all these very nice presentations that are on the agenda. And I think from what I've seen, they will be informative for both sides. And I also hope that the format of this workshop, which is now virtual, is not impeding on the ability to discuss as we normally will do it within a workshop. That's the spirit of it, to have enough discussions so that we really can share as much as we can. So initially, the idea was to have maybe an in-person workshop, but now this has been jeopardized by the pandemic, as you all know. So I really would like to take this opportunity to thank the team that has been behind the organization of this workshop. I should name here France. She has been spearheading this, and also I should name Jacques David and Roman Hatsky. So thank you all for this great effort in putting this nice agenda together, organizing the concept of the workshop and contacting the speakers. And in the end, I wish to thank all the speakers for providing us the opportunity to listen to what you have to say and what you have prepared, and for putting all the time available to us. Thank you very much. And with that, I think I would like to conclude this introduction and wish everyone a very nice workshop, a very productive meeting. And in the end, I mean, if you have any suggestions for improvement for the future, please go ahead and provide them to France in particular. And we will think about maybe how to improve if any suggestion is made. Okay, thank you, France. The floor is back to you.
Thank you, Richard. So the next talk in our agenda is given by Yasushi Todo from NIFS Japan, and the title is Comparison between GFRS1 and NIFS Supercomputer. Richard, I think you need to allow Mr. Todo to share his screen.
Indeed.
Yes. Can you hear me?
Yes, we can hear you.
Yes, Todo-san, we can hear you very well.
Nice to meet you.
Nice to meet you again. Thank you.
Thank you.
We can see your screen to the sun.
Thank you very much. Okay. Thank you for this nice opportunity given. Let me giving a talk at the IFERC Workshop on GPUs Programming, and I am very happy to join this meeting. And I am also sorry I will not talk about the GPU. I run my simulation called Mega on JFRS1 at IFERC CSC, and the plasma simulator at our institute, National Institute of Fusion Science, and Fugaku. Fugaku is a Japanese national flagship supercomputer. Okay, this is my outline. Okay, first I will introduce computers I used, JFRS1 and the plasma simulator and the Fugaku. And I will introduce simulation called Mega. It is a hybrid simulation code for energetic particles and MHD. And talk some part of optimization of Mega. And I will report Mega performance on plasma simulator and Fugaku and compare the performance among JFRS1, plasma simulator, and Fugaku. Okay, let me start with JFRS1 at IFERC CSC. Okay, JFRS1, you can see the picture on the right. Is a Cray computer, Cray XC50, and the total nodes 1,370. And the CPU is Intel Xeon Gold 6148. And each CPU has 20 cores, and each node has 2 CPUs. So the total 40 cores per node. And the peak performance is 4.2 petaflops. It is at roughly 3 teraflops per node, and the total 4.2 petaflops. And the total memory is 256 terabyte. An advantage of JFRS1 is a big memory per node. It is 192 gigabyte per node. And interconnect is Cray company's original network, ARIES, interconnect, and the data storage 27 petabyte. And in the top 500 list, it is ranked 119th. But when the JFRS appeared first in June 2018, it was ranked 61st. Okay, next I will talk on plasma simulator RIKEN at our institute. The right figure is the picture of the computer, and RIKEN means God of thunder in Japan. So it is named after, so named was open to public, and so many people voted to the name, and it was named RIKEN. It is good to simulate plasma, so with the god of thunder. And the computer is NEC SX-Aurora TSUBASA A412.8. And the total nodes, it is vector host. It is a Linux machine, 540 nodes. And each host has one CPU, AMD EPIC CPU. And each node, each host has 4 vector engines. Vector engine is a vector processor. And each host has 8 vector engines. And totally vector engine, 4,320 vector engines. And the total performance is 10.5 petaflops. It is 2.4 teraflops per vector engine. And the total memory is 202 terabyte. Each vector engine has 48 gigabyte. And advantage is the memory is HBM2. It is a very fast memory, and the memory bandwidth is 1.35 terabyte per second for one vector engine. And interconnect is InfiniBand HDR200, 2 InfiniBand for each vector engine. For each vector host. And node to node, vector host to host, interconnect is 800 gigabyte per second for bidirection. And the data storage 32 petabyte. And it is now ranked in top 500 list. It is 33rd. And for the HPCG high performance conjugate gradient, it is ranked 10th. So compared with the top 100 ranking, so the plasma simulator has a good performance for HPCG. Okay, and it is a brief description of vector engine. A vector engine is a vector processor, and it is connected with PCI Express card to the host Linux computer, and with high memory bandwidth, 1 terabyte per second, and vector engine has 8 cores and 6 HBM2 memory modules. So this results in high memory bandwidth. And NEC is now selling the many types of vector engine computers, and now NEC sells vector engine to other companies such as Visual Technology and Halifax International. You may refer to the web page of NEC. And I introduced Fugaku. It is a Japanese national flagship computer. It is, I heard this is a product of a Fujitsu company. And I heard that hardware of Fugaku is the same as FX 1000. It is sold publicly. And the total nodes, it is 158,000 nodes. And the CPU is ARM-based CPU, Fujitsu's original CPU. It is A64FX. And SV means that it was scale. I will talk later. And it is an ARM-based CPU and 48 cores per CPU. And peak performance is 500, more than 500 petaflops. Each CPU or each node has 3.3 teraflops performance. And the total memory, 4.8 petabyte. And the memory is HBM2, same as the NVC SX-Aurora, and achieved also high memory bandwidth. And the interconnect is Fujitsu's original top network. And now it is ranked first, top in top 500 and also in HPCG. Okay, next I will talk on MEGA. It is a hybrid simulation code for magnetic confinement fusion plasmas. And it is a hybrid code with gyrokinetic energetic particles and full magnet hydrodynamics. And energetic particles and MHD are coupled through energetic particle current density in MHD momentum equation. It is called current coupling model. And the numerical algorithm is fourth order finite difference for MHD and for Runge-Kutta for time integration. And it is parallelized with MPI and OpenMP. And simulation domain is decomposed in three-dimensionally, alpha z direction. And also we have a particle decomposition, but usually particle decomposition is not used and not used for the benchmark case. I will talk today. Okay, and MEGA uses employed a hybrid simulation. It is for energetic particles, it is particle in cell simulation. And in the particle in cell simulation, it is peak simulation for plasmas. Particle location and velocity is allocated to grid and calculate charge density and current density and pressure. And on the other hand, electromagnetic fields on grid, electric field and magnetic field, interpolated to the particle position, location, fields on particles. So N is the index for particle, electric field and magnetic field. So then the access, memory access is generally it's random and not sorted. So the memory access is the key for high performance computing for peak. And so in MEGA, we use sorting, sort of particles with respect to grids. But so there is a trade-off of sorting. So if we sort well the particles, the performance is good, but the sorting itself demands a computational time. So as of now, we perform sorting once per 10 time steps. And also, what is important is vectorization for plasma simulator. It is, of course, it is a vector computer, and also SIM for JFRS1 and Fugaku. In my understanding, vectorization and SIM are very similar. And okay, so in the MEGA, subroutine push is most demanding. It is a subroutine to move and accelerate particles. And this subroutine consists of the 5 steps. And the first step, these are electric field array defined in 3-dimensional grid points, R, Z, phi direction. And it is once these arrays are copied to one array with M is an index for the field, electric field and magnetic field and other field for calculation of weight of particle for delta F method. We use totally 30 arrays. 30 fields. And we should find the grid where each particle is located and the interpolation coefficients and interpolate fields on particle from this array FLD to FLP is the array of field at particle location. N is the index for particle. And then calculate the increments for particle location and the velocity for each particle using this FLP. So this procedure makes the memory access more efficient. And so we avoid if bifurcation inside the loop. And another demanding subroutine density, it is this subroutine distribute particles to grids, and especially for it is important for plasma simulator, a vector machine. And I think this is a popular method for vector computer. For example, when we calculate particle density DNS, we use a working array here, WKDNS. It is a 4-dimensional array extended with some 1 dimension for vectorization. And this loop is for particle, and this loop is called skipped by the size of the vectorization array, vectorization dimension. And we have basically this is totally the number of particles, loop for total number of particles, and it is divided into double loop. And inside the loop, this is here is the loop for the extended dimension. And first we calculate this working array by WKDNS. So this loop can be vectorized because it is independent for M here, MN. And then so we sum the this working array to compute the density array. So also again we can this loop is vectorized. So totally these calculations are vectorized. So it is important and popular for vector machine, vector computing for particle simulation. This is so very important for plasma simulator. If this process is not vectorized, the performance is very, very low. So this vectorization for subroutine density is very important. Okay, so I report the performance on plasma simulator of Mega. Here we use these are grid points I used. And here I used relatively large number of particles per grid, 1,000 per grid, and used 256 nodes. It is 2,000 vector engines. It is 16,000 cores. And we use flat MPI for parallelization. And we see these three subroutines are more dominant, push density, and the last one is for Runge-Kutta for time integration. So these are three subroutines have cost 80% of the total computational time. And the push is runs most fast with 35 gigaflops per core. Its performance is ratio of the performance to the peak performance is above 11%, very good. And for density, subroutine density, so we vectorized with vectorization technique for plasma simulation. It is we have 2.6%, and the time integration is most slow. This is a very simple loop, but inside the loop, the instruction is very few. We have very few number of instructions, so the efficiency is not high. And totally, we have 6.5% to the peak performance. And the vector operation ratio is very good. So the code is very well vectorized. And next, I will talk on performance on Fugaku. I use the 2000 nodes. It is 98,000 cores. And on Fugaku cost, each node costs over 48 cores. And from the hardware, it is recommended to use 12 OpenMP threads and 4 MPI process and 12 threads for each node. It is recommended based on the hardware information. And we have also performance, total performance 4.4%. It is also good. And it is a scalable vector extension. It is a kind of extended stream. Its operation ratio is also good, but for subroutine density, it is not good. This is because for this subroutine, I used another optimization for Fugaku, and I put priority for the OpenMP parameterization, and it is not vectorized now, so the performance is not good. Okay, so this slide summarizes the result. Okay, for plasma simulator and JFRS1 and Fugaku. And horizontal axis is the peak performance, and the vertical axis is the result performance. And for plasma simulator, we investigated both weak and strong scaling, and we have good scaling, almost linearly increasing with the increasing peak performance. And for JFRS1, also a good scaling. And for JFRS1, I used only 20% of the total system. So if I use the total JFRS1 system, its peak performance is 4 petaflops. So we will have a data around here. Okay. And for Fugaku, I used only 2,000 nodes, and Fugaku, it is only 1% of the total system. If we try big scaling study, so we will have a much higher performance. I expect such high performance with Fugaku. And right figure shows the efficiency ratio of performance to peak. And for plasma simulator, it is good above 6%. And Fugaku, it is 4%. And JFRS1, it is a standard Xeon computer. We have 2.5%. Finally, I would like to talk physics. The reason why I'm using relatively large number of particles per cell, 1,000 per cell. So it is I am interested in the analysis of distribution function. And for fusion magnetic confinement system, this is velocity space is 2-dimensional. So if we expect okay, for 2-dimensional resolution, 30 times 30, so it is about 1,000. So I'm using 1,000 particles per cell. And these figures show the time evolution of distribution function in RG plane. And along E prime is constant. E prime is a combination of energy and toroidal canonical momentum. And so this clarifies the resonance interaction with alpha eigenmode and energetic particles. And linear phase and nonlinear phase, we see the flattening of the distribution function. And such a analysis of the distribution function is important. I am now expecting to promote such a distribution function analysis with supercomputers. Okay, now I come to my summary. Performance of Omega is compared among JFRS1 and Plasma Simulator and Fugaku. And good performance of Omega is demonstrated for both strong and weak scaling on Plasma Simulator. And Omega achieved about higher than 6% of the peak performance for on Plasma Simulator. And the performance of Omega on JFRS1 and Fugaku is 2.5% and 4.4% respectively. And I'm still working for optimization, more optimization, and expecting improved performance in all the computers. Okay, now thank you very much.
Thank you very much, Todo-san, for your talk. Any question from the participants? Please unmute yourself if you have a question and go ahead.
Hello, this is Simpa Kaslanpro from Finland. Thank you for the great talk. May I ask, how long time steps are you taking with energetic particles to keep them roughly in the same domain decomposition cell?
I'm sorry. So for domain decomposition, I could not catch your question.
The push part of your simulation. How long time steps do you push? Because I
this
quickly move from one cell to another.
For this case, it is I simulated 5,000 time steps, and for Plasma Simulator, it took 1,000 seconds. So it is for 1 second, 5 time steps. But
for the simulation time or the physics time or the particle, how long is the particle time step in particle time?
It is physics time, physical time. It is very short. 5,000 time steps is very. Usually, I am running the code for typically 1 million times. 5,000 time step is very short.
Right. So 1 nanosecond per time step or 10 nanoseconds.
Yeah, it is one. Yeah, that's right. One nanosecond is a good estimate.
Thank you.
Thank you.
Okay, so Leo, I see you have a question. Please unmute yourself.
Yeah, may I ask, the Fugaku is an ARM machine, so is there any special coding concern when you are moving your code from a CPU machine to this ARM machine?
Basically, so yeah, basically the same code. Just the compiler do everything, and basically I run the code on JFRS1 Geonc, and the same code can be run on Fugaku. And for better performance, I do some optimization, but maybe without optimization, maybe Mega will run with half or speed, at the speed half of the optimized speed, I think.
But what kind of optimization have you done? You changed some coding, or you need to tune your compiler?
It is mainly, yes, mainly tuning of the do loops. So divide do loops to several parts, or so one loop is divided to double loop. Such a loop deformation is effective.
Okay, thank you, Todo-san. So I see you, Thomas, having a question. Please go ahead.
When you reported the performance of the different machines, you were scaling it to the peak performance, but the
yes.
I would argue perhaps that the novelty of these machines is the memory bandwidth. And given that this perhaps is what you're seeing, if you were to renormalize these figures where the performance was normalized to the memory bandwidth, would this then explain the difference? Is this the key parameter for the performance that you see?
I agree with you. So for comparison between plasma simulator and Fugaku, the difference is well explained by the difference by memory bandwidth. And for JFRS1, it is JFRS1's memory bandwidth is much smaller, I think. So the JFRS1 is working better than its performance of memory bandwidth.
Thank you.
Okay, thank you.
Any other questions for Todo-san?
I have a question, like comment to support Thomas' question. I think it will be nice because you have so large calculation to plot a roofline model where you are as not only performance but also the bandwidth will be seen. Then you can, yeah, you can see what you can squeeze from your hardware. Yeah, just a comment. It will be nice to see.
Yeah, memory bandwidth is very important. I agree. Yeah, thank you.
Okay, so is there any other questions?
I will come back to the first question, maybe not the first, but the second.
Okay, please.
Now, that was a question by Leo. With regard to adapting your code on the Fugaku, so you explained that you basically optimize by changing the structure of the do loops.
Yes.
So the question is, in terms of workload, I mean, how will you quantify this? I mean, first, do you see it as a heavy workload? And second, do you still see that you can further optimize compared to what you already have? What is your final impression on the Fugaku?
It is okay. For Fugaku, I have a collaboration with a Fujitsu company, and I heard they spent 1 month with one person, with a specialist, and did optimize. And I learned their knowledge, their technique, and implemented in this version. And so maybe what I can do is, so I choose the frequency of the particle sorting. Now I am sorting it once per 10 time step. So, but we can, so I check the time for the sorting is, now it is only 1%. So we can do more frequently the particle sorting. So this may improve the total performance. Such a minor point I am planning for Fugaku.
Okay, so how, if you had a layman, for instance, somebody who doesn't have the support from a Fugaku specialist or expert, I mean, if you take anyone from the Fusion community now, he's trying to get his code adapted to Fugaku, what will you rate as the expected workload for him? I mean, how difficult is that going to be? What is your expectation?
Yeah, it is. But what I said is so very so one specialist for 1 month. It is so very high level optimization. And so what I said is so the code for running on JFRS and Geon computer, it can run as it is on Fugaku, and the performance, the improvement in performance is at most double. So the program code, every code can run so on Fugaku, so without such sophisticated optimization.
Okay, thank you very much, Todo-san, for sharing
Thank
your
you very much.
experience.
Thank you. We have, I'm sorry guys, we need to move on, so we have room for one more question. Yagi-san, please go ahead.
Todo-san, can you hear me?
Yes.
Okay. My question is, you maybe remember the more than 10 years ago, your present simulator is real vector machine SX. If
Yes.
you compare this SX-Aurora and maybe SX6 or 5 or something, how much is the peak performance in all days? Did you remember?
Yes, yes. So for all the days, so that in the time of Earth simulator, so more than 10 years ago, so the performance ratio to the peak performance for my code was about 20%. And now it is 6%, yeah. So now I'm expecting a slight improvement, but the total, anyway, the performance is reduced. So half or 1/3 compared from the previous old supercomputer, vector computers.
Okay, so in old days, so memory is very fast, right?
Yes, very, very fast. Now it's good, but it's byte flop is roughly 0.5 for Aurora SUBASA. So it is now not so good compared with all the machines.
Okay, thank you very much.
Okay, thank you, Dirol. We will move to the next talk. So the next talk is given by Siri Moshalski from HDST. He's from Max Planck Institute for Plasma Physics in Garching. So give me a second, I will give you the authorization to share your screen, Siri.
I think I see already this red button.
Okay, so have a try.
I just try it. So can you see my screen?
You can see your screen. Perfect.
So now I suppose it's full screen.
Yeah, it's full screen. Thank you, Siri. You can go on.
Okay. Hello, everybody. My name is Serhiy Mochalsky, and today I would like to present my work, Benchmarks and Validation of the Marconi 100 HPC system. Full presentation today will be dedicated to this device. It is a schematic view of the Marconi 100 Power 9 GPU node. This one node consists of 2 sockets with 2 CPU from IBM company, Power 9 CPU per node, 1 per socket. 4 NVIDIA Volta 100 GPU cards are connected to one Marconi 100 node with 2 GPU cards per socket. One CPU consists of 16 cores with possibility to have hyper-threading modes with 4 threads per core. All nodes in Marconi 100 partition are connected between themselves by means of Mellanox InfiniBand EDX Dragonfly interconnect. Connection between 2 CPUs, 2 sockets is done via link, so-called X-bus connection. The next CPU is connected to GPU, as well as 2 GPUs inside one socket connected between themselves via connection from NVIDIA company named NVLink. And finally, main memory is connected to the CPU via PCI Express bus. In today's presentation, you will see different tests and benchmarks which are dedicated to test and to find the performance and the bandwidth of each individual component what I presented. Before I move to my benchmark, I would like to show you where I executed my test. It is not the full Marconi 100 system. This complete Marconi 100 supercomputer consists of 980 nodes. However, all my tests I will execute it only on the Eurofusion part of the system, which consists of 80 nodes. These 80 nodes are divided by 4 racks with 20 nodes per rack. I started with my test, and first benchmark I executed in order to test main memory bandwidth. Marconi 100 node has access to 256 gigabytes of the RAM memory per node, 128 per socket. The memory bandwidth is formed via 8 memory channel with a memory bandwidth of 70.5 gigabytes per second per channel. So in total, we will have a bandwidth of 140 gigabytes per second per socket, and in total 280 gigabytes per second per node. In order to test this main memory bandwidth, I use a benchmark, one of the most famous in a HPC community, named Stream Benchmark, on a single Marconi 100 node. Here on the figure, you can see the bandwidth versus the number of OpenMP threads. Blue line here represent the Marconi 100 node. For comparison, I include in the figure my result from the Marconi SKL partition, represented here by the green line. And as well, I used this Marconi 100 node in hyperthreading mode, represented by orange line. All three lines has typical compact pinning distribution for the stream benchmark, but most important that if I use all available cores in the node, I was able to reach 266 gigabytes per second of the main memory bandwidth on Marconi 100. That is around 95% of the theoretical value. If we compare this result to Marconi scale partition, I was able to reach only 203 gigabytes per second, and it's less in the theoretical percentage. Also, when I used hyperthreading mode, orange line, in total, using the all available cores and thread, I get a little bit less result in comparison to the mode without hyperthreading. We were quite happy with this result, and then we decided to launch the stream benchmark concurrently on all available Marconi 100 nodes dedicated to the Eurofusion part. And here on the graph, you can see the bandwidth versus the relative node number. And here, each blue cycle represents independent node. And as you can see, all nodes provide very high and stable bandwidth, with the average value around 266 gigabytes per second. Marconi 100 supercomputer has a possibility to share one node between several users. For example, two users can use independently two different sockets inside one node of Marconi 100 node. Therefore, we decided to execute the same stream benchmark, but independently on each available Marconi 100 socket. And here on the graph, you can see the bandwidth versus a relative socket number of Marconi 100 node. What we found the similar result as before, that all sockets provide very high and stable bandwidth close to the theoretical value. We found this was the main goal of this test, no difference between two sockets inside one node. So it proves that two users can use two different sockets inside one node independently, and they will get the same main memory bandwidth of around 133 gigabytes per second. I finished my test with main memory bandwidth, and now I came to the test of the GPU card itself. As I said in the introduction, Marconi 100 node equipped with 4 NVIDIA Volta 100 GPU card with 4 per node and 2 per socket. Each card includes 16 gigabytes of the internal RAM memory. This capacity is not so big in comparison to the main memory, where we have 256 gigabytes. However, it's much higher in terms of the bandwidth. This memory has a theoretical bandwidth of 900 gigabytes per second per card. And if we compare to the complete SKL node, the theoretical bandwidth of the complete SKL node is 255 gigabytes per second. So there is factor around 3.5, almost 4 between one GPU card and complete SKL node. The same happens in the peak performance. The theoretical peak performance of one GPU card is 7.8 teraflops. And if we compare the complete SKL node, the performance there is 3.2 teraflops. So here we have factor of 2.5 if we compare again full SKL node with one GPU card. So the result, the theoretical values are quite promising. And now we wanted to test these values. The first, we test again the memory bandwidth of the GPU card. And here on the graph, you can see the GPU bandwidth versus the relative GPU number. For this test, we used modification of the stream benchmark from IBM company named Babel Stream. And we run this benchmark again simultaneously on all available GPUs on Marconi 100. As you can see, we were able to reach really stable result, and all of them are very high and close to theoretical value. We found no difference between two distinct GPU cards on different nodes or two GPU cards inside one socket. We were able to achieve 845 gigabytes per second of the theoretical bandwidth, which is around 94% of theoretical value. When we tested the bandwidth, next step, we wanted to test the performance of this GPU card. And here on the graph, you can see a performance in teraflops versus the relative GPU number. For this benchmark, we used a DGM benchmark, double precision matrix multiplication benchmark developed by IBM company. Here on the result, we can see two different parts of the distribution. In the first part, which include half of the node, 40 nodes from two different racks, our distribution are really stable and flat. And other half of the result from another 40 nodes from two other racks provides us a bit higher result, but as well with small fluctuations. We contacted Marconi support team why such situation happens, and they reply that in order to guarantee more stable production, IBM advised them to manually set up a GPU frequency from target 1 to reduce the GPU frequency from the target 1312 megahertz to 1250 megahertz. And such procedure at the moment of this benchmark were done only on the half of the racks. Therefore, half of the nodes provide us a bit lower but stable bandwidth, and half of the nodes provide a bit higher but with small fluctuation. In the current time, this procedure should be finished in all racks, and we should get very stable bandwidth everywhere. Nevertheless, our peak performance, what we measure, was very high. We were able to reach 6.7 teraflops, which is around 86% of the theoretical peak performance. For example, on the SKL node, we were able to reach only 2 teraflops with our benchmark. So there's factor more than 3. Now we came to the benchmark for our connection and links between CPU to GPU and between I think we should mute microphones.
Can you mute?
Leo, you are unmuted. Leo, you need to mute. Sorry.
Okay, thank you.
Thanks.
So now we came to the part of my presentation where I would like to present you my test and benchmark dedicated to different connection between computing units, different computing units of the Marconi 100 node. And first of all, I would like to show you a test for the connection between CPU and GPU and between two GPUs inside one socket. This connection is done by means of NVLink connection from NVIDIA company. It is already its second generation. The bandwidth is formed here by means 3 memory channel with 50 GB per second of the bidirectional bandwidth per channel. So in total, we could achieve 150 GB per second of the bidirectional connection or 75 GB per second of the unidirectional data transfer. For this test, I use a benchmark from NVIDIA company named NVLink benchmark. And I executed this benchmark again concurrently on all available GPU card of Marconi 100 Eurofusion partition. Here on the graph, you can see the bandwidth versus the relative node number, and picture to the left represents the connection between CPU to GPU, and picture to the right, vice versa connection between GPU to CPU. On each figure, there are 4 lines. Maybe you cannot distinguish these 4 lines because they are on top of each other, but there are 4 lines which are represented result of different GPU cards inside one node. So we have 4 GPU cards and we have 4 connections between GPUs to CPU. As I said already, in our result, we get very stable and symmetric bandwidth because this all 4 lines of different result from different GPU are on top of each other for both CPU to GPU connection and GPU to CPU connection. We also got very high memory bandwidth. We were able to reach unidirectional bandwidth in around around 67.2 GB per second for all available power of CPU to GPUs, which is around 90% of the theoretical value. The next, we wanted to test connection between 2 GPUs. And we use the same benchmark, NVLink benchmark. And on the figure, you can see the result again, bandwidth versus the relative node number. First, we tested the bandwidth, what we call it intra-socket bandwidth, between 2 GPUs which are located inside one socket. Here is blue line. And as we can see, our distribution again has 2 parts. It's due to this reduced GPU frequency, what I discussed before. Nevertheless, we reached to very high and stable bandwidth. We were able to obtain around 136 GB per second, which is 90% of the theoretical value between 2 GPUs inside one socket. However, when we measure 2 GPUs on different sockets, here the message should go through 3 different connections. First, it should go through from one GPU to CPU through the NVLink connection. Afterwards, it should go from one socket to another one through the X-bus connection, and finally from another socket to GPU back from NVLink connection. And from such a message path, we were able to achieve 40 GB per second of the memory bandwidth. And it's a bit lower result than we expected because, as you remember, we tested a NVLink connection on our previous benchmark, which I come back now, and here we were able to reach 67 GB per second. So it means this 40 GB per second is limited not by NVLink connection, but X-bus connection. And X-bus connection has theoretical memory bandwidth of 64 GB per second. So there is still some room of optimization, and we contacted Marconi support team, and now together with IBM and NVIDIA support, we are investigating this result, and we will look in the future how we can optimize them. Next, I wanted to test the internode network performance of the Marconi 100 supercomputer. As I said in the introduction, the internode connection is done in Marconi 100 by means of Mellanox InfiniBand connection. With the bandwidth of around 100 gigabits per second, 12.5 gigabyte per second of the bidirectional memory bandwidth. In order to test this memory bandwidth, I used another benchmark named Ohio State University, also micro benchmark. And I used uni and bidirectional bandwidth test from this benchmark. Here on the graph, you can see the bandwidth versus the message size. In this benchmark, I sent messages of different sizes between two computing units. In this case, between two nodes of Marconi 100 partition. In the result, we can see that our bandwidth increased with increasing the message size as we expected. We were able to saturate both unidirectional and bidirectional data transfer with a message size around between 2 and 4 megabytes. We were able to reach stable and high bandwidth with around 99% of the theoretical value for the bidirectional data transfer, and 100% was measured for unidirectional data transfer. Also, we decided to test two different combinations of the node location. In the first combination, we use so-called closed physical node location. We executed our test on two Marconi 100 nodes, which are located inside one rack, physically close to each other. And in second test, we executed our benchmark between two nodes, which are located far away physically from each other in two different racks. We call it this combination remote one. But we found no difference in our results here. They are on top of each other. So we were again quite happy of such benchmark and our achievement. The next, we wanted to test one more time connection between two CPUs inside one node. And this connection is, as I said in introduction, named X-bus connection with maximum memory bandwidth of 64 gigabytes per second of bidirectional data transfer. I use the same benchmark as before, also micro benchmark. However, here I send the messages between two CPUs inside one node. On the graph, you can see as before bandwidth versus the message size. And what we figure out that the bandwidth increase with increasing the message size as before, as we expected. However, afterwards reaching some higher message sizes around 2 megabytes, the bandwidth decrease. And it saturates afterwards for some large message sizes. In the beginning, we thought it's some kind of bug, and we investigated this this problem in more detail. We'll relaunch our benchmark using different compiler and different MPI library. We used GNU and OpenMPI, and as well XL compiler with Spectrum MPI library, but we found no difference in the result. In the collaboration with Marconi support, NVIDIA and IBM, we figure out that it's actually not a bug, it's a feature and advantage of the cache. And this bandwidth increase to such a high value only because we have cache in these CPUs. And such a distribution happens everywhere in all systems with a cache. And afterwards, the bandwidth start to decrease due to the cache misses. And when cache misses becomes dominant and all messages are quite high and they are quite large and they are reading from main memory, the bandwidth is saturated with some a bit lower value. If we wouldn't have cache in such a system, our distribution will not have this peak at all and will saturate directly to the low level. So it was figured out that this is not an issue, but a feature of any system with a cache. Lastly, in my presentation, I would like to present you the real code stability performance. In all my previous tests, I used a benchmark, which is kind of artificial codes which are dedicated to measure the maximum what we can obtain in the performance and in the bandwidth. And here I wanted to test the real code execution of Marconi 100 nodes. And here I would like to thank to Thomas Hayward and Mariela Ippolito for helping me with their code to compile, install, and prepare this benchmark of Marconi on Marconi 100 nodes. For both codes, I use the maximum available number of nodes of Marconi 100, 16 nodes, and I used 64 MPI tasks with 64 GPUs. Let's talk first about ORP5 code. Here on the graph, you can see the real work clock time in minutes versus the relative run number. And our result, we should distinguish by two parts by this red line, before Marconi maintenance, which was 11th of June, and afterwards. Before the Marconi maintenance, I got quite stable result if all allocated nodes for my calculation were from one rack here. However, when I took for execution nodes from 4 different racks, the execution time increased by more than 25%. We informed Marconi support team about this issue, and they were already aware about it. And the problem was the not optimized algorithm for the data exchange between the nodes in located on different racks. During that maintenance, they adapted a so-called unified fabric management with adaptive routing algorithm. And after this update, after the Marconi maintenance, I repeated my tests, and they provide really stable result. Here you can see independent from where I allocated the nodes for execution, from one rack or from 4 racks, I got really stable result without any fluctuation. And the same happens with LAMPS code. So I got really stable result from different run of the LAMPS code. The last result, what I would like to show you in my today's presentation, is the usage of Marconi 100 system. As you have seen during my presentation, I executed a large number of tests and benchmark, and not all of them were presented today. But the most of them, or almost all of them, provide us very stable and high result. However, people don't really use, we figure out that users don't really use Marconi 100 system. Here on the figure to the left, we can see the number of the node used of Marconi 100 over the whole operation period of the Marconi 100 supercomputer. Violet color represent here when system is idling, and green color stands for the Marconi 100 allocating nodes. As we can see, there was never time, never day when the Marconi 100 was completely used by 100%. It starts from the beginning, very low number of users and very low usage of Marconi 100. Afterwards, it's increased a bit during limited number of time, during 1 week, something like this. And afterwards, it's decreased again and stay very low, on the very low level. We had even few days without 0 usage. So few days the system stayed completely empty. And we have positive trend in the end of November, but however, still it's far away from optimal usage. If we take a look in the high temporal resolution of 10 minutes, here the picture to the right represents result of 1 day. I choose 1 day somewhere in June. We can see the typical result for HPC systems. That during the night time, we have a low usage, and during the midday, we have a bit higher usage. However, even in the most busiest time of the supercomputer between 11 and 12 o'clock, we never reach 100% of usage of Marconi 100. There always were a few nodes idle and ready for calculation. And here is a general conclusion of my presentation, today's presentation, that Marconi 100 system works pretty well. All my tests shows quite high result in terms of bandwidth and performance. However, the system is barely used by scientists, and I advise you to launch your code there because it's empty and schedule will accept your job directly. Thank you for your attention.
Thank you very much, Siri, for the talk. Guys, participants, any questions? So I see Leo, you have a question. Please unmute.
Yeah, have you tried to compile the lamps with or without the NVLink? How are the difference on performance?
So it was like some internet problem. You asked how if I tried the lamps code run without NVLink?
Oh, this one is without NVLink, you mean?
No, this code is with NVLink. I run it on a GPU card, and we must have NVLink connection because CPU.
No, I think if you compile the lamps, you need to specifically to switch on the NVLink support if you want to have the NVLink support for lamps. So I just wonder if you have compared the result with or without the NVLink support for the lamps code.
No, I don't have such comparison.
Okay, thank you. Is there any other question for Siri? And if so, please unmute.
So, hello, this is Yoichi. I'd like to ask you about the stream Babel bandwidth measurement on GPUs. Which version do you use to measure the bandwidth on GPUs? Because Babel stream should have multiple versions like CUDA version or Corpus version or PGI version. So which version do you use?
So this version, I'm not sure what they used inside. I used from IBM company. It's named Babel Stream. And I suppose they used CUDA as far as I remember.
Sure. Thank you.
Okay, thank you. Any other question for Siri? Okay, so I think we can close this talk. Thank you very much, Siri, for giving this very good talk. So the next speaker is Asahi San from the Center for Computational Science and E-Systems CCSE in GAEA. And so the title would be Accumulating Knowledge for Performance Portable Kinetic Plasma Simulation Code with Cocosing Directives. Okay, thank you, Asahi-san. And when ready, you can start.
So can you see my presentation?
We can see the presentation and we can hear you. Thank you.
Okay, thank you. So thank you. I'd like to first thank the organizer of this meeting and also for my collaborators from France, mainly from Seoul and also from Maison de la Simulation. So I'd like to talk about the recent work for toward the performance portable kinetic plasma simulation code with directives and higher level abstraction. So I'd like to introduce the plasma turbulence simulation. Most of you may know very well about it. And this type of first principle gyrokinetic simulation is used to model the plasma turbulence and to know more about the confinement property of fusion reactors. The problem here is the very high temperature of the plasmas, which exhibit non-Maxwellian particle distribution. So in order to model this kind of plasmas, we need to solve the full distribution function. Fortunately, we have some sort of the approximation to reduce the full 6-dimensional distribution function into the 5D, but still it is 5D. I mean, there is 3-dimensional grid points in this space, like the electrostatic potential shown here. And each point we have the velocity space. So in total, 3-dimensional real space and 2-dimensional velocity space and 5D stencil computations as provided by the Nomura-san's figure in 2009. And another issue is solving the machine scale problem with the turbulent scale mesh, which means that in the degrees of freedom is up to the 100 to the 5th into the 10 to the 10th. So this already requires the petascale supercomputing. They are concerning the dynamics of kinetic electrons or complicated geometry. So even more computational resources required. So accelerators are the key ingredients to satisfy huge computational demands at reasonable energy consumption. This situation is often regarded as MPI plus X, and this talk is related to the explorer for the X from our group. This is the outline of my presentation, but I'd like to introduce what is the demand for MPI plus X for our group, and introducing the G0 code and mini apps, and also what we did for the Cocos and OpenCC and OpenP version for the mini app, and how do we optimize and how we implement the mini app, and obviously the result is also discussed. And then I move on to the MPI prioritization of the mini app and the update of the algorithm, and also for the some sort of optimization on the OpenCC version and also Cocos version, and finally show the performance and scalability, and just summarize the future talk. So I'll begin with the introduction. So this slide summarizes the demands for MPI plus X in the group. So namely the readability and portability and productivity and high performance.
And there is a small window on your slides that's hiding part of your slides.
So which one? Small, where does it locate?
Small window named downloading a file since, and we see that on your screen.
Where I couldn't see from my screen. So where does it locate? I don't know.
We see. Yeah. Okay. So now we don't see it anymore.
Okay. So maybe just I don't know which one is better. So this is okay for you, or?
That's fine. It's big enough. Thank you.
Okay. So in the group and here, what we need is readability and portability and productivity and high performance. So as you know, the portability is getting more and more important because in the exascale supercomputers may be very divergent, like the EARM machine on Fugaku in Japan and the GP machine summit, and including Marconi M100 on Italy. So the exascale machine could be very divergent. We need portability desperately. Another important issue is the readability, because our code should be readable and writable for the physicists, which means that in the should be very easy to read and should be very understandable. So the directives also benefits for this purpose. The productivity is also a major concern, because as in the recent development of G0, we just moved from the circular geometry to the limiter geometry. So we often want to advance the realistic physical to be the more and more realistic physical model. So the productivity of the code is kind of major concern. And of course, in our code should exhibit very high performance, and this shows the strong scaling of the zero code up to 112 kernels, plus MPI plus OpenMP polarization, and a strong scaling is excellent with some sort of overlapping technique. And the reason is that we use more than 1 mega CPU hours per year, so our code must be very high performance. And in order to satisfy some of them, is not that difficult, but all of them at the same time could be very difficult. So there are a couple of approaches which satisfy these demands. It may include the directive-based approach like OpenMP and OpenCC and OpenMP 4.5, or a higher level abstraction like Cocos, Raja, or Alpaca. And I would like to try these kind of approaches on some devices, the NVIDIA GPUs, Intel CPU, and ARM CPU. In this talk, and at the very beginning, we use the Thunder X2 as the ARM CPU. The later of the talk, I tried the A64FX as a new type of ARM CPU. So this slide summarizes the zero coordinates. The full detail is described in the Virginia's paper 2016 CPC. And the physical model is just modeling the ion temperature gradient turbulence. And recently they extended to model the kinetic electrons, but in this token, not quite relevant. And this calls solve the 5-dimensional Brasov equation coupled with 3D Poisson equation and solving the full gyrokinetic equations. The numerical scheme is using the same Lagrange as named and to solve the Brasov equation. And the interpretation of the footprints just performed by spline or Lagrange interpolation. Polarization of this code is just formed by MPI plus OpenMP with 3D domain decomposition by MPI. The fairly good scalability up to 450 kilocores is great, and more than 50 kilorines in Fortran 90s, which makes some of the work difficult. So in this token here, we just encapsulate key G0 features into mini-app. I mean, the G0 is just very complicated, realistic tokamak geometry with complex numerical scheme, where the polarization is just MPI plus OpenMP, quite normal, quite the most simple one. Language is Fortran, and the lines of code is more like 50 kilorines. So we just move on to the simpler version of the mini-app, which means just encapsulate the key features into mini-app and solving the 4D Brasov equation to then coupled with 2D Poisson. The geometry is far simplified to the periodic boundary conditions. The scheme is quite similar, just using same Lagrangian and Lagrange interpolation, and operator splitting is the first version of the mini-app. And the first version of mini-app, we just don't use MPI, but we tried quite many X as OpenCC and OpenMP and the Cocos. In order to use the Cocos, we need to move on to the C++, which is kind of required a little more work, and lines of code is quite suppressed. And because we didn't try the MPI, the first version, so we also tried to parallelize with MPI, and the current version of the mini app just parallelized with MPI, and slightly different numerical schemes without operator splitting. The mini app is preferable because we need to suppress the work, but the parallelizing with Cocos or OpenCC and the entire G0 code is quite difficult. So we just try to minimize the work and to parallelize with such an advanced way. And also we can try some sort of advanced implementations of our algorithm, like the Lagrangian without operator splitting, which is kind of very compute intensive. And in the first version, we tried OpenMP 4.5 and OpenCC and Cocos. And in the new version, we just tried OpenCC and Cocos because these two directives or Cocos as a better option to parallelize for GPU and CPU. And our sample code of the mini app is available on GitHub. So if you're interested, please look at it. So this is the testbed description. I don't go for detail, but in I use the P100 GPU and the B100 GPU and the Skylake machine. And for the reference bandwidth, we use the stream bandwidth we measured using the Babel stream and also for the normal stream, and also for on SandX2 and something like this. And as you can see, there are relatively low byte-over-F ratio around 0.1 or up to 0.3. And so suitable for computer intense kernel is quite useful for the recent supercomputing. And just a high diversity found in the L2 cache, number of cores, the byte-over bandwidth for GFLOPS. And different compiler careful compiler options are quite important for this work. So this slide summarizes the description of the full kernel. I don't detail every kernel, and there are a couple of advection kernel because we just solve the 4D advection equation in Brasov equation with strong splitting. So each operator is just solved around the one dimension, which improves the performance quite a bit. And also for another one is the velocity space integral and the 4D to 2D and in the Poisson equation. This is just the equation, and it's more like the memory bandwidth test. Although they perform the flop over byte is quite same for the advection kernel in each direction, They are quite different in terms of the cache because or vectorization, because the where the indirect access happens is quite different. So this should be divided into the 4 kernels. And the integral kernel just here reduction by row and memory bandwidth test. So this is the baseline OpenMP implementation of the advection kernel along X direction. So you can see there is 4-dimensional loop along each direction, and the outermost 2 loops are just parallelized with OpenMP by clocks 2, and this is something like this. And around along X direction, there's some sort of non-contiguous memory access coming from this Lagrange interpolation, something like this. This should be a clear bottleneck in this kernel. The good aspect of this kernel is relatively high F/B ratio. So it's around 4, it's quite good in high compute intensity. So this should be bottlenecked by this complicated non-contiguous memory access from FN. So this is the OpenMP baseline version. So for the OpenSCC, and there are some, unfortunately, we cannot use the data structure in the OpenSCC at that point. We just implement here Cocos-like view class, which is the simplified version of view to have the high-dimensional data structure. When at that point, and this view doesn't work in the accelerated region, so we have to get the raw pointer and just use raw pointer in the innermost group. From the accessor, just compute the high-dimensional indices by ourselves. When just we parallelize the outermost 3 loops by class 3 and the innermost loops in vector independent in the OpenSCC implementation. And this implementation is coupled with OpenMP version into a single merged version with called OpenMP OpenSCC implementation. So I introduce Cocos, the very basic part. So the key feature of the Cocos is the abstraction. Some of you already know, in the Cocos just abstract some sort of the parallel operation, and they offer the parallel abstraction of the parallel operation, including parallel for and parallel reduce. So this is the major two types of the parallel operation are available in the HPC context, and these are 2 relevant parallel operations. And the execution space, the operations are performed on GPUs or CPUs mainly. It could be FPGA in the future, I don't know. The execution policy means how the operation is performed. There is the range policy and team policy, and I just tried the high-dimensional range policy for optimization. So this is coming from the tutorial. So we can just define some sort of operation by ourselves in functor or lambda, and like this, and define operator, something like this. So in this case, just the parallel execution pattern is parallel reduced. So the reduction operation is performed in parallel, and the range policy is just the single 1-dimensional range policy, and compute this operation in parallel. So this is just how the Cocos parallel operation works. Another important abstraction is the memory abstraction called view. So the major difficulty is coming from the best layout of the 2-dimensional array or high-dimensional array may be different for the OpenMP and the CUDA. I mean, the most important point for the OpenMP parallelization is just in the outermost direction should be quite independent to parallelize with OpenMP, while the innermost direction should be very contiguous for the SIMD optimization. So in that sense, and the best layout for this AIJ array may be contiguous in J direction and non-contiguous in just in I direction. So the best layout may be the raw measure order. So this is more like C style is preferable for OpenMP. On the other hand, and for the CUDA backend, we may want the contiguous access along the I direction, because in CUDA you need to map the threads to the innermost direction for the better performance. In that sense, and the I direction should be contiguous, which means that in the current measure order is preferable, which means that the AIJ is defined as the just Fortran style. So we need that in for CPUs, the C style is better, or for GPUs in Fortran style may be better. So we need that in here. These arrays should have different layout which is determined by compile time, and this is enabled by Cocos by layout abstraction. So this is the Cocos version for the high dimensional root support, and for called 3D range policy. And this is the 1D functor we defined for the computing the OpenMP, so the previous OpenMP implementation of the Lagrange interpolation. And just the implementation itself is quite similar. The major difference is coming from this part. So we define the MD range policy, the 3D policy. We just define the range to compute the parallel operation like this. And also the characteristics of the MD range policy is the availability of tiling. So we just define the tile size by this Rust argument. And we can just parallelize the OpenMP just means 3D tiling like this. Just 3D loop is parallelized with something like this. And in CUDA, means 3D thread mapping. So the parallelized like this, and grid is defined by this, and block is defined by this. So CUDA kernel is executed by this way. And this is quite beneficial on CPUs because this facilitates SIMD on CPUs and beta cache uses on GPUs. So this is key feature for the optimizing Cocos kernel in our experience on the mini app version 1. This slide summarizes achieved performance in terms of the roofline model, and we just show the relative performance to the stream bandwidth stream triad. As you can see in the Cocos and Bruce, and the red values mean red figures mean just the Cocos performance on the Skylake and Sando X2 and P100 and B100, and blue and just the OpenMP and OpenCC performance on each kernel. So each kernel shows the more like some of them just shows the more than 80% to the peak performance, which is quite nice. And this is also true for GPUs, which means that in as shown here. And OpenCC OpenMP performance is not as good as the Cocos version, and they also has pretty good performance except for the Sando X2 on the OpenMP version. So, but in that sense, and some of them are unsatisfactory, but most likely, and we got fairly decent performances both implementation. So in short, and we achieved performance portable implementation with Cocos and directives like this. And we target for the Brussels-Poisson equation, operator splitting. And Cocos allows us to just define a single kernel which works on CPUs and CPUs at the same time. And the performance gain from the baseline of this Skylake, we got performance something like this. And the original version of the OpenMP is just 278 seconds. And finally, we got the 6.79 at the B100 and with Cocos. And the B100 is actually pretty good, and more accelerations obtained with both in Cocos and the OpenCC. And the major benefit is just the abstraction memory and for operation offered by Cocos. So at this point, we are quite satisfactory about the performance. We have to move on to the MPI prioritization, which we got the more like unsatisfactory performance, unfortunately. To go for the MPI prioritization, we also try to explain a little about the one-time step algorithm. So the major difference is coming from the prioritization, which offers the MPI communication of this the FN array. And first, we all move on to the spline interpolation. Then we also have to compute the spline coefficients, which is kind of terrible operation because we need to have the read and write dependency along some direction. So this memory access pattern is also terrible. And another point is the integral is just quite the same, and also followed by the MPI reduce, which is inefficient. And for the advection is just performed one time in this kernel. So just this kernel has the extremely high flop over byte, but in the memory access pattern is not good because of the indirect memory accesses. So this slide shows the flop over byte of each kernel, and as you can see, the spline integral kernel is quite memory bottlenecks, And the direction 4D and direction 2D is relatively compute intense. But the memory access pattern is not great because of the indirect memory accesses. So in order for better readability, we newly developed the OpenCC view with layout abstraction. As I said before, we need to get a row pointer because views, our previous version of views are not accessible in the accelerated region. So we had to get the row pointer and use row pointer in the in-out region, which is not good to see and harm readability quite a bit. The new version is just available inside the OpenCC accelerated region, and as well as caucus and the contiguous dimension can be specified at compile time, but we don't highly rely on this feature in this talk. And also we just confine the host data use device and programmer inside here, this wrapper for the FFT. So the entire code is shortened quite a bit and more readable right now. So this slide summarizes the new testbed description, and the format two are quite same, and the JFRS machine and Rokkasho and TSUBASA for the GPU testbed. And the floor machine is the new one and using exactly the same CPU on the Fugaku machine with its A64FX. And this is more like the high memory bandwidth machine on relatively low gigaflops. So this is relatively high byte overflop ratio in the end. So, and also the network connection is quite good in the floor machine. So I'd like to move on to some sort of the optimization with our new view class on the OpenCC and OpenMP version and the Cocos version. So the optimization for the directive version on F64FX, I just tried the quite naive optimization, basically CPU optimization. So they are just targeting the velocity space integral like this, which means their F is just integral over velocity space and get density. So just parallelize some sort of loop along the Y direction, and the innermost direction in the X direction is parallelized with vectorized with CMD programmer, and just the innermost two directions just reduce the velocity space direction, as you can see, and just store the density buffer and obtain the value. So just here for the optimization, we just tried the strip mining with CMD loops. So just splitting this IX loop into their vector loop like this. So introducing new vector loop, actually, this makes the compiler to understand the code a little bit better. And we got the 3.31 acceleration of this optimization. And also they applied this kind of strip mining and CMD optimization. We got the factor 1.5 and 1.15 on the other kernels. So this type of optimization is relatively good on the A64FX, where the obtained performance is still quite unsatisfactory. We'll propose two optimizations for Cocos version, including tile size tuning with Cocos and coupled with MD range policy, another layout tuning. So as I told before, we launched a Cocos kernel, and the range policy is defined by like this. So the last argument means tile size. So as you can imagine, the performance is highly affected by the tile size. So particularly on their CPUs. On CPUs, just default tile size is chosen as 4 in each direction, and GPUs something like this. And the reason why we choose this kind of tile size on GPUs is that there is magic number for CUDA. The 32 is not equal to the warp size, so the 32 is quite clear to be the best number, or something like that. So we just scan the elapsed time with respect to the tile size. So because the best tile size should be affected by the architecture or problem size and something like that. And run the kernel with the best tile size and get the Windows performance. And another tuning is the layout optimization. So I just tried the layout left and the layout right, so which means the C layout or Fortran layout of each array. It turned out that the layout left is better in terms of the total elapsed time, and this is due to this is more cache effective. because their 2D operation is performed around the two innermost loops. So the layout rate is more cache effective in that sense. This is also the case for the 4D kernel. Layout integral kernel is not that effective, but it is exceptional. So in the end, the layout left is better in terms of performance. As expected, and for the tile size tuning, after tuned, we got 1.1 acceleration on CPU in some kernels, and their slight acceleration on GPUs. So this approach shows the inverse elapsed time with different tile size for the advection 4D kernel. On CPUs, this graph can be shown that this reaction is the tile size of X, and this reaction is tile size of Y, and this reaction is tile size of BX, and each process shows the different tile size along the VY direction. So as you can see on there, it's more like the random and we cannot expect which one is a better tile choice. So it's pretty difficult to expect in the GPUs. On the other hand, on GPUs, as expected in there, we have the quite clear the localized value around the TX equal to 32, which is equal to the warp size on the NVIDIA GPUs. So as expected in this is the reason why we don't get their huge acceleration on GPU, because in there we already have a great tile size as a default. This is not the case for CPU, so we got a relatively high acceleration on CPU with this tile size tuning. This slide shows the achieved performance, fix this problem size, and we just try to measure different number of CPUs or GPUs in order to fix the number of nodes. So on Skylake, and the 8 MPI processes correspond to 4 CPUs or 2 nodes, and the matrix should be something like this, and they're relatively low memory bandwidth, but in the relatively high cache size. And A64FX only 2 CPUs, was 1 CPUs, and there are 4 MPI processes are carried to that. So this is just 2 nodes. And for 2 nodes, and the GPUs are just 8 GPUs, so quite many, because in one node there are 4 CPUs as well as numerically 100. And just a quick summary, we got relatively high performance on the Skylake OpenMP version and the P100 OpenCC version around some sort of kernel over 50% to the peak bandwidth, peak to the roofline model, and also for some sort of Cocos kernel is also good. But in this case, in Cocos version is less good, probably due to the 4D range policy is not that as sophisticated as the 3D range policy. The terrible performance found in the A64X version, as you can see in the less than 3% in the OpenMP beta version. In the Cocos version is much worse, which is quite unsatisfactory. So and this is partially due to the smaller cache size, which is quite normal, because in the cache size is relatively low compared to the Skylake version. But the more problematic part is the usage of C++, and the compiler is not fully matured to optimize C++ code, and some sort of inline functions are not fully optimized, so we almost get no optimization effect in the A64FX machine right now. Even for the simpler version of the OpenMP version, the Cocos version could be much worse, because they cannot interpret Cocos version quite well. So in the end, we try to measure the performance portability metric proposed by Pennycock like this, and this metric means they're just for some application on some simulation setting, and just measure the performance on the set of platforms. In this case, just P100, A64FX, and JFRS formats or the Skylake machine. And just summation of the size of the set is equal to the absolute value of H, and just divided by the efficiency, and then we got the performance portability metric. The efficiency can be evaluated based on the roofline model. So in that sense, we got relatively low value of the performance portability, because the roofline estimate is the most strict and the most difficult to get a good value on that. And the performance portability on Skylake and the A64FX and the P100, we got the relatively low value, and in the parentheses, it's without A64FX, which shows relatively good performance portability, both with OpenMP and Cocos version, when the F64FX has a clear difficulty. This may skip in the just to demonstrate the how does it scale to up to the some sort of number the CPUs, and the both version shows the relatively quite scalable feature except for the P100 because their performance is already quite good at the very beginning, and some of the kernels like the spline or spline computation and the peer-to-peer communication do not scale quite well as expected. So we're in the F64FX and their communication is quite good and they're quite scale quite well, but this is mainly due to the raw performance on that. So let me conclude my talk, and I just tried the directive-based approach, the mixed OpenCC and OpenP for the one example to get their performance portable version on CPU and GPUs, and achieve their high performance in the marginal on A64FX, and they're suitable for porting large legacy code like Z0 and more than 50 kilolines of code. And introducing OpenCC build to improve the readability, and which works quite well. And SIMD optimization like strip mining may be critical for CPUs, including A64FX. The higher level abstraction is Cocos and quite helpful for simpler kernels in the mini-app version 1, but little less efficient for the more complicated kernels like what we showed for the MPI version of the mini-app, and not working quite well for the A64FX. An appropriate choice of the execution policy seems critical for CPUs. And layout and tile size tuning may improve the performance when cache matters. We are currently want to submit a paper of this work, but the further optimization of A64FX could be critical. And maybe then the CRAN compiler may be helpful. But I'm currently investigating this point. And thank you for listening. That's it from my part.
Thank you very much, Asai-san. So any questions? I see, Siri, you have a question. Please unmute.
Hi, here's Sergey. I want to ask my question regarding to the slides 26. Can you maybe go there? Which compiler do you use on the AFX64 node? You said
we use the
Fujitsu compiler, yes. Okay. And the second question again regarding to this slide 26, you stated that usage of C++. Is there any difference in usage of Fortran? Did you check the compiler of Fujitsu is better working on IFX CPU with Fortran code, or there is no difference between C++ and Fortran there?
Yeah, Fortran version outperforms in general. For example, if you like to measure stream bandwidth with Fortran code, it's 10% better than C++ version for some reason. This is one thing. And another is that in the C++ code is probably highly relying onto the inline functions, as you may expect. This may not be truly the case for Fortran. This may be just related to the code style in each language, when this type of inline functions are not fully optimized on the A64FX with Fujitsu compiler, which may often result in the raw performance with C++ code.
And maybe you have any knowledge, are they going to optimize their compiler, Fujitsu?
Since we are not quite good at the Fujitsu compiler, and we are not very familiar with Fujitsu compiler, because okay. I myself just didn't expect that in the inline functions doesn't work well. It's quite embarrassing. But anyway, in the we have quite good knowledge about intercompiler and the NVIDIA, where I'm not very good at Fujitsu compiler, and in my opinion, it's not fully matured. So there's almost no choice at this point. Maybe in the future, it could be improved. At least I hope.
Thank you for your answer.
Okay, thank you. I see, Thomas, you have a question. Please unmute.
I had a question on slide 23 with the strip mining that you show.
Yeah.
of course, putting in the, let's say, the manual strip mining for the vectorization is not something that you would want to have to do. You have to deal with then the remainder cases for anything which doesn't exactly divide 8, I guess, but also the readability, I guess you would, I would argue, goes down from the top case to the bottom case. So is this simply that the compiler is not doing a good enough job with the vectorization? And do the recent vectorization statements in OpenMP help this? If you put, instead of OMP SIMD, if you start putting vec length and dependencies, could you get the compiler to do this? Or is this really just the compiler is not effective enough at vectorizing?
I may say that for the intercompiler, I guess, and the vectorization could be well performed by compiler and some sort of programmers. But no, for this compiler, we have to make the code as easy as possible for the compiler to understand. So currently there is no choice, but I hope in the future and some sort of directives work well to optimize. I don't know at this point right now.
Okay, thanks.
Any other question for Azai-san? Yep, Leo, go ahead.
Yeah, it seems you suggest Cocos has a better performance than the OpenMP and OpenACC, right? But would it be a reason of the compiler?
So, well, actually in at the very first try for the mini-app version 1, which employs the simpler algorithm and simpler kernels, we saw that in the Cocos version is better, where in the little more complicated version, we got the better performances of OpenACC. So, but probably due to we have changed a little bit about the AMD range policy, and which may harm the performance quite a bit. So we have to make further optimization with Cocos to be fair. Where in I think in if the kernel is getting more and more complicated, the final performance may be close, I guess.
Okay, any other question or comments for Azai-san? Okay, I think not. Thank you very much, Azai-san, for your talk. And let's move to our next speaker, who's Thomas Hayward Schneider from Max Planck Institute for Plasma Physics in Garching. And the talk is titled The Gyrokinetic Plasma Particle in Cell Code OP5 on GPU platform, such as Marconi 100 and lesson learned. Thank you, Thomas. So please go ahead.
Thank you, Franz. I hope you see the slides full screen. Please interrupt me if you don't.
Yes, we see full screen. Thanks.
Okay, so I am going to give a version of my presentation, and this is not the right version of the slides. Okay, it's only a minor difference. Okay, so I would like to talk very briefly about some of the experiences that have been made by using the code OP5 on GPU platforms. So a rough outline of the talk is something about the code OP5, something about the work of putting OP5 onto GPUs, something about mixing CPUs and GPUs, and something about the issues that we've faced. I try not to present any kind of sales talk. I try not to give simply a rant. I try to talk about some features, some things that were done, some issues, and some outlook. So background, what is OP5? OP5 is a global gyrokinetic electromagnetic pit code. It has markers, or otherwise known as particles, which represent the phase space. And the fields are represented on a finite element mesh. And in the way that it's solved, this is then Fourier filtered. And this is somehow relevant to the performances. And I'll come back to this a little bit later. The code has been around for quite a long time. I mean, it's based on Fortran and MPI. And in recent years, the code was modernized, refactored, and ported to OpenMP and OpenACC for many multi-core and GPUs. And this work was done Sorry, I just want to change to the correct version of the slides. Okay, this should be the, okay, this is better. And this work was done by the Swiss Plasma Center and with input from CSCS, the Swiss National Computing Center. And this work was reported in this CPC paper of Noe Hana from this year. The code in general is, and the state of the code is, in a relatively recent state is reported by this paper in CPC of Emmanuel Lanti. A word on the parallelization on the code. The code has 3 levels of parallelism. There's domain decomposition, which is essentially MPI distribution of different toroidal planes in the plasma. There's the second level is domain cloning. This is simply saying that if the first level doesn't offer enough parallelism, then we duplicate the machine essentially in the way that it's represented, such that each new clone of the machine only has then a smaller number of particles. So you can think of this as a particle only decomposition. And then the third level, this is the new level, this is the multi-threading or with OpenMP or OpenACC for the GPUs. A word perhaps on the cost or some assumptions that we might make about the performance of the code. There are certain contributions to how expensive a simulation is. There's a term which is somehow proportional to the number of particles present in the simulation. There's a term that's somehow proportional to the size of the grids in the simulation, where this is perhaps a bit vague, but somehow goes with the size of the grid. There are some perhaps small constant terms, and there are perhaps some terms which depend on both of these factors. So let's look a little bit in this. In terms of the particles, when we push the particles and when we look at the particles, we assume that this is linear in the number of particles. When we're solving the fields on the grid, well, some parts of this are linear and some parts of this are based on Fourier transforms. So this is something like linear or n log n, depending where this n may or may not will be some subset of this grid for one of these dimensions of the grid. And then there are operations which map the particles to the fields. So there's the fields putting their charges or their currents onto the fields, and there's the particles getting the fields from the field arrays. And these perhaps depend on both, but in practical terms are approximately linear in NP, the number of particles. To leading order, the biggest term is probably, I mean, we assume that the largest term is proportional to the number of particles. And the next term would certainly depend on the grid resolution. But of course, it depends on simulation parameters exactly how these two terms scale. But for the time being, at least, we'll assume that the number of particle term is the dominant term. In terms of parallelizing the particle operations, as I just mentioned, we split by the toroidal planes. It doesn't have to be splitting down to one plane, but this is often the case. So that would set the maximum parallelization by toroidal plane. So this would go to something like several hundred way MPI parallelism. We can duplicate the system, so create clones of the plasma, and this could be arbitrary level of MPI parallelism. And then each plane clone, so once we've done this, that object will run on one MPI rank. And so for when running in pure MPI mode, this would be one core. If we're running on open MPI and open MP hybrid, this would be on several cores. And if we're running on a GPU, this would be one core of the CPU plus one GPU. And I'd like to come back to this point here towards the end of the talk about not limiting the code to one core when running on the GPU. And originally, the multi-threading, so this final stage, this was only applied to the particle operations. So what does it look like in terms of decomposition? So if we imagine we have essentially a cube in logical space of the 3 spatial dimensions, this is the toroidal dimension. We cut up the domain like this. So, and then this doesn't give us enough, so we just duplicate the whole thing again, and that's cut up in the same way. So in this case here, we would have 8 MPI ranks, these 8 objects here, 2 clones, and 4-way decomposition. And then within one of these objects, which is perhaps thin now in the toroidal direction, but broad in the radial and the poloidal direction, we have one MPI rank, and that has OpenMP or OpenACC for the markers. And aside, a word on OpenACC. What is OpenACC? How does this help us or not? It's a directive-based paradigm for GPU offloading. It's a single source model, which offers us large advantages to keep the code as a single source code. But it still it creates some burden for developing the code in terms of making sure that when working with the code that the various versions of the code still do the correct thing when making some change, that we don't accidentally break something else. And I would say that whenever dealing with any CPU and GPU enabled code, some type of automated testing framework is essentially mandatory. OpenACC is essentially supported on NVIDIA hardware for GPUs, and it's essentially only supported on the NVIDIA compiler, which is formerly the PGI compiler. There is some level of support in other compilers, but not sufficient for our needs. And in recent years, so very recent years, OpenMP has sort of caught up with most of the features that are provided in OpenACC, although the support of this is varied. Well, the support of both are varied, but this is perhaps something one could think of in the future, that to use the features of OpenMP for GPUs, which exist somehow parallel to OpenACC, but very similar. Okay, so these are some figures that I took from the paper I quoted earlier. If when doing different decomposition, this is a test case, increasing the toroidal decomposition and changing the clones or the number of threads, we see that the best performance in this case comes from OpenMP hybrid. This is running on a Skylake node, and that is faster than running on the fastest pure MPI example. And we see that the different subroutines in the code are affected different ways, because of course when doing the OpenMP, this is applying only to the arrays which involve the parts subroutines of the code which affect the particles. So that's the deposit, the get field, the gyro average, and the push. When running on a GPU, here is some comparison. So this is Skylake. This is exactly the same case that was on the previous slide. This is on a Power 9 node. These results were taken from Summit. This is Power 9 plus the V100 GPUs on Summit, and this is Haswell plus P100. These are the GPUs on Pisdaint in Switzerland. We see that the code is much faster, but we see that what becomes dominant term becomes the field solver. So what's marked in red is a relatively small contribution on the CPU, because it becomes a relatively large contribution on the GPU. One could argue that given that the field solver is not particularly particularly fast and it's not accelerated, that for this particular case, we should run on less parallelism or fewer GPUs. But unfortunately, the memory capacity of the GPUs is actually sets a minimum level of parallelism. And this is a point that I'd like to come back to later. So part one, a summary of part one. OpenACC has relatively effectively accelerated the particle parts of the OB5 code on GPUs. It's somehow too successful. I mean, not too successful, but it's sufficiently successful that these parts of the code are not now necessarily the dominant terms. And as an additional point, I would like to point out that the limited memory capacity on the GPUs becomes somewhat of an issue, because now we have a lower bound on the amount of parallelism we can use for a particular problem. The particles are living only on the GPUs, and this reduces the communication. And in terms of the actual amount of directives that are included in the code, it's relatively, well, it's very small. There are approximately 500 OpenACC directives in the entire code. I'd like to talk a little bit about mixing OpenMP and OpenACC. So previously, at the moment, or previously, the code was using one or the other for some technical reasons. And we have in the code OpenMP and OpenACC directives around particle loops. And when compiling for CPU, the OpenMP directives are used. And when compiling for GPU, the OpenACC directives are used. A question came up this year: can we accelerate when we're running on the GPUs, an operation which is difficult to port onto the GPU. So and the answer, or the aim would be to try and do this operation, accelerate it with OpenMP. So a brief aside of an example of what some code samples might look like. So this is a particle loop, and we have then some OpenMP directives around the particle. And we can build the code with OpenMP turned on in order to enable it, in order to use it. Alternatively, we have some directives that look like OpenACC directives, same loop, and we compile the code instead with OpenACC. And so in reality, we have essentially the loops double wrapped. And because they're wrapped around the same loop, we can't compile with both directives. So suppose we wanted to do, for example, this accelerate with OpenMP, this loop, which is not on particles, but is on something else. The question is, how can we compile this if we want to run this one on the GPU and this one on the CPU? So let's say the first step that we can do is, let's just sort of ignore this for a moment. So I'll turn the OpenMP directive into simply a comment. And now we can compile this happily because this loop only has one set of directives on it and this loop has a different set of directives on it. But of course, I've broken this somehow, right? This now no longer is an OpenMP directive. And so this is one way to do it. Another way to do it would be with excessive preprocessor directives. But essentially what we say is, if we're not using an OpenMP, then we ask the compiler to rewrite this back to being a normal OpenMP loop. And this affected all of the previous OpenMP directives on particle loops. So an example, why would we want to do this? Well, this year, Peter Donnell has written a new nonlinear collision operator in the code, and this collision operator was ported onto the GPUs. And when running, he wanted to use the quad-tree smoothing operator, smoothing algorithm, and this algorithm doesn't work on the GPU, and it would not be necessarily be an easy task to port this operation, this algorithm, to the GPU. So the version -1 is that the code simply crashes if you call the subroutine, because the particle data is living on the GPU, and so the code will crash. Version 0 would be to check if that the quad tree is disabled when compiling to the GPU. This doesn't actually help us compared to the -1, but at least the code doesn't crash. Version 1 would be, if we want to call the quad tree algorithm, we first copy the data from the GPU to the CPU. Then we run in serial, we run the quad tree algorithm, and then we copy the data back again. And this is slow. It serializes the code, but it works. And if we're calling this algorithm very infrequently, then maybe this is fine. Unfortunately, if we want to call this algorithm every single time step, then this is simply not an option. And so this is what the version 2, this is what we now have. We're going to start an asynchronous copy of the marker data from the GPU to the CPU. And then for each species, we wait to see if that species data has already arrived. When it has arrived, we call an OpenMP threaded version of the quad tree algorithm. And then we start an asynchronous data transfer back from the CPU to the GPU. And then we wait until all of the transfers are finished. And so this combination of OpenMP plus OpenACC plus asynchronous data transfer, even though we're now having to copy data from GPU to CPU and then back again, this is now at least acceptable, even if the quad tree is called at every time step. And just for some numbers, a very simple test, a toy test that I did, I measured the number of steps, time steps that the code evaluated in a fixed amount of time. And with the algorithm turned off entirely, I got 131. With the slow version, this came right down to 40. And with the version 2, this came back up to 98. So this speed up, or the amount that the reduction in slowdown was factor 3. A more realistic case, let's say the real case, this was run on Daint and PysDaint, and here now a set fixed problem and measuring the time. And without the quad tree turned on at all, we had 687 seconds. This, of course, got very much slower when running the slow version, but this comes somewhere back close almost back to the original performance with this second method. So the slowdown in this case was reduced by a factor 6. And whilst this isn't perfect, of course, this is now somehow a reasonable cost for this algorithm. Some issues. I mentioned before the memory limitation. So 16 gigabytes per GPU is not a very large amount of memory on the GPU. And given how quickly the GPUs are able to push particles, this very much affects the performance because we simply are not able to fit in enough particles to be able to push given the other costs of the code. So we would like to fill up the GPUs as much as we can with markers. However, sometimes we overfill them and this crashes. Sometimes the code then restarts and it has no problem. And if we try and log the memory usage, we see various fluctuations over time, and this is very difficult to understand and or to debug. And I don't know whether this is related to OpenACC. I don't know whether this is related to buffers, but this is somehow a mystery. And so in practical terms, this means it's difficult to use more than about 2/3 or 3/4 of the GPU memory because we don't want the fluctuations to cause the code to crash. If I look, this is a very small figure, but this is time in minutes and GPU memory usage. And these four traces are 4 different GPUs of the same simulation. And this is the output from the NVIDIA SMI tool. These jumps here are very difficult to explain, and this doesn't even necessarily reconcile directly with the runtime memory debugging options. And so this is somewhat of an open problem, and if anyone has any experience with this, then please get in touch. In terms of the support, we are tied to only a single compiler, which was PGI, that's now the NVIDIA compiler. And this is the only compiler with sufficient OpenACC support for what we have. We have some outstanding compiler issues. So the latest version of the compiler causes crashes when for the code. So I have to compile with an older version of the code. And the parallel version of the HDF5 library, which we use for output, this library never will work properly for our needs on Marconi 100. And in fact, in the end, I rewrote parts of the code in order to avoid using this library. For multi-vendor support, in the long term, one could think about migrating from OpenACC to OpenMP 4.5+. As I mentioned earlier, this has very similar features to OpenACC. This is something which one could consider on the timescale when we want to run on a hardware platform which is not supported. So this is not an immediate plan, but this could be a long-term migration plan. In general, I'd like to say a few things about scaling. So there's the scaling in general is affected by what I said earlier. So the assumptions in that performance slide that I showed earlier. So essentially the balance between particles and grid. And this depends on the physics that we want to study. Now, unfortunately, the very physics that I'm interested in is somehow the worst affected because at least when running linear simulations, we have a very large grid and not necessarily an enormous number of particles. But this is certainly not always the case. As I think we saw earlier when I showed you the slides from the GPU, the strong scalability of the code is affected by the field solver, and that's true on CPU as well as GPU. And when running on the GPU, then at least then mixing OpenACC and OpenMP could be an avenue to help here to get better than the serial performance of the field solver. And a slightly more fundamental point, GPUs are somehow very effective with throughput rather than latency. And somehow one can map throughput to weak scaling and latency to strong scaling. So we should never expect necessarily that a small simulation should get faster, but simply that a bigger simulation might take the similar amount of time to a small simulation when running GPUs. And with that, I'd like to summarize. So the code was ported to GPUs with the use of OpenACC. The particles live on the GPUs. The rest of the code is on the CPUs. The details are in this paper of this year. When running on Mark Only 100, but also on many other machines, the limited GPU memory capacity is certainly a limiting factor. And this sets either a minimum parallelization for a certain problem or a maximum problem for a given number of, for example, for a given number of nodes. The strong scalability is now that the particle operations are very fast, the strong scalability is now typically limited by the field solver, and perhaps mixing OpenACC and OpenMP, as I've shown, can be done in this presentation, could be seen as a path forward to help with this. Thank you very much.
Thank you very much, Thomas, for your talk. Any question for Thomas? Yeah, I see you, Simpa, so please unmute.
So, hi, thank you again for the talk. It was very good. About the particle pushing, how many, can you estimate how many markers you need to fill your GPU to keep it fully occupied?
It's something about close to 10 million. It depends a bit on ions or electrons because of gyro rings versus non-gyro rings. Part of the work that was done and detailed in this paper traded memory use, increased memory usage for ease of getting the gyro rings working nicely with GPU memory. Because of course, with a gyro ring, you have some kind of non-local memory access. And so this is this algorithm that is implemented is slightly more memory intensive than is perhaps nice. So I forget if it was 10 million per GPU or 10 million per species per GPU, where we typically have 2 or 3 species. So it's something like 10 to 30 million particles per GPU. Because we have a memory footprint of more than 1 kilobyte per particle.
Thank you.
Matthias, please go ahead.
Thanks. So really nice overview. I was interested, maybe I missed it, and I apologize, but for the OpenMP 4.5 plus option, which you mentioned, would you consider this already a feasible option right now for a new development? So basically, how does the compiler support in that respect look like?
I was hoping to connect to the UK OpenMP 2020 meeting a few weeks ago, where a couple of people from NVIDIA gave a talk on the NVIDIA support for OpenMP offloading. Mm-hmm. From what I can tell, reading around, the support certainly is not far behind OpenACC in the worst case, and is probably better in the best case. And where support is lacking, it's certainly catching up. And of course, with OpenMP 4.5, you have Intel support for Intel GPUs. You have promises of some support for AMD GPUs, although this is much less clear. So you're not tied into a single compiler, but you're also not tied into a single hardware.
So the Intel compiler in principle supports it already, just not yet necessarily for all GPUs yet.
The Intel compiler supports it for Intel GPUs, either external or integrated. Mm-hmm. The NVIDIA compiler supports it to some extent for NVIDIA GPUs. The IBM compiler supports it very well, actually, for NVIDIA GPUs, to the extent that well, I'm not sure how this copes with certainly modern language features for Fortran.
Okay, thanks.
So I think, I mean, other projects, maybe Simple wants to say something, but other projects, for example, Ascot, went down that line, but I believe that's based on a C code base rather than a Fortran code base. But there's certainly, if you look around, you'll find presentations from Oak Ridge, from IBM, of offloading with IBM compilers onto Summit for GPUs with OpenMP 4.5. And more recently, then, for example, there were the talks by NVIDIA at, for example, the recent workshop, but many others this year.
Thank you. So we have now a question from Siri. Please go ahead.
Hi, Thomas. Thank you for a nice presentation. I have comments or question about the mixing OpenACC and OpenMP. Will do you have any idea, will Cocos do the job for you, maybe, if you will integrate it in all the loops?
As far as I
basically the question, can we use the Cocos like for different loops, different hardware that these loops?
I'm pretty sure Cocos can do this. Sickle definitely can do this, and Sickle and Cocos are not so different from each other. Of course, for our purposes, Cocos is a C++ framework and has some but limited Fortran interoperability. And therefore, sticking with something that's primarily Fortran based is certainly an attractive option. But in the more general case, yes, I think Cocos can do this.
Okay, thank you.
And thank you. Now we have a question from Peter. Please go ahead.
Okay, thank you, Thomas. A question concerning the use of OpenMP for GPU. If you use OpenMP for GPUs, could you also mix the use of GPU and CPU as you would do with a mix of OpenACC and OpenMP?
Yes, this is almost easier because OpenMP has lets you put some if clauses into the constructor to decide whether they're running on the GPU or not. So you can even have the same OpenMP directives which are applied, which do slightly different things if you're doing GPU offloading or if you're running on the CPU host.
Okay, thank you.
Thank you. Any other question for Thomas?
Yeah. So as for the field solver or new collision operator, is it impossible to get good performance with GPU?
So the field solver is, in many sense, in my opinion, is in many sense too simple or too cheap in order to get effective performance on a GPU. It's necessarily going to have relatively large amount of parallel communication, and it's based on Fourier transforms and Fourier filtering, both in the plane that's on the GPU and also the plane that's MPI distributed. So one could conceivably do the in-plane Fourier transforms on the GPU. But then again, we come back to the question of memory capacity. Does this cost more in memory capacity in order to do this, which is really a critical factor, than it would help? And I think there's a lot of optimization can be done with threading of the Fourier transforms on the CPU at the same time as, of course, we necessarily have the communication for the toroidal FFT. And of course, the GPU will never help with this because this data is distributed.
Yeah. Okay. And this is just another question, but I'm very interested in getting an environment for the PGI compiler and MPI on the Marconi M100, because I'm quite new to that machine and I couldn't really get there. How do we construct PGI environment there? So if you know more about it, I'd like to know that point.
So what used to be the PGI compiler, the PGI 19.10 compiler version was recently retired, but is still available in the archive. However, but this compiler was replaced by the NVIDIA HPC SDK, and that's available as a compiler module. Unfortunately, as I mentioned, there are some issues related to launching, which occur when the code launches with the recent versions of these libraries. And these libraries also, and I also had a lot of issues with the more recent version of the compiler building the HDF5 library. And that had nothing to do with this code. Simply the tests would fail when building the HDF5 library. That's now resolved with I think the 20.7 version of the NVIDIA compilers. But now I see a different problem, and Chineke are in communication with NVIDIA to try and solve this problem. But if you want to know more about the compiler, then environment, send me an email, and I can say something to you.
Okay, thank you. So because in there, I desperately need the CUDA MPI environment also, which is sometimes difficult to construct.
Yeah, it's difficult to find compatible versions of MPI and CUDA and compilers. Yes.
Yeah.
Thank you very much. Any other question for Thomas? Okay, so I assume it's a no. Could you? Thank you, Thomas. So next point in the agenda is the virtual group photo. So I invite all of you to turn on, please, your camera, and I'll do my best to have all of you. So give me a sec. Richard, it would be nice to have you on screen. Okay, so let's wait a few minutes. The time I have almost everyone. Richard? Okay, so let's take this one. Thank you. I have the full screen. Okay, and keep smiling, I'm coming. And there it is. And got it. Thank you very much, everyone. I appreciate. This is the new online networking. Okay, so let's go back to the agenda. Sorry, give me a second. Okay, so next point in the agenda, well, it's open discussion and questions. So we still have about 15 minutes to discuss any question or any topics you would like. So what I can propose is that we can go back to the question asked previously that we could not answer during the talk. So we can discuss, for example, the NeckVector compiler if you want to, or there was also discussion about the ARM compiler. So please, guys, go ahead.
Maybe I ask then the same question I asked about the strip mining and the vectorization of the with the Fujitsu compiler. Would these problems be handled better with the ARM compiler?
Pretty much hard to say. I've never tried because in the only environment I could use for the ARM compiler was the Sailor. I don't remember the exact name, but in the SX machine offered by Sailor, and I can no longer use that machine right now. So I have no idea, but in the definitely it will be, as far as I'm concerned, for the C++ compiling and the ARM crank is much better. And the definitely C and the intercompiler outperforms for sure. The intercompiler is just a masterpiece, and this isn't. So, yeah.
Okay, thank you.
So as I said, maybe I have a question also on ARM. So I'm not really familiar with this ARM environment, but
yeah.
What's the state of software for debugging, profiling? Because what I have in mind is Intel software.
Oh yeah, for this offers the debugger at least, and also for the optimization, they have the profiler. The profiler itself is quite good because in the they offer quite detailed information. But in the I have never tried because the problem here is just the code itself is not fully optimized, which is just found on the compiler optimization messages. they also always show that and say that in their Discord is not well optimized because of this issue or something like that in there. So after we got the reasonable compiler messages, I will go for the further optimization with profiler. But we are not in that stage right now.
Okay, thanks. So guys, any other topics you would like to discuss? For the record, I am thinking about it. At CA, we have, or we will have in the upcoming days, a small ARM cluster with the A64 FX nodes, but part of them will be later in 2021 will be moved in BXI interconnect. So that will be interesting because I know that some of our researchers have access to Fugaku computers, so we can test several software environments and also hardware. We would be able to test BXI, InfiniBand, and Tofu performances and ARM environment and the Fujitsu software environment. So if any of you are interested in accessing this machine, please let me know and I see what I can do to help you accessing this machine. It might be interesting if you want to make tests.
So what kind of compilers are available there?
So that there will be, normally there will be the ARM compiler suite. I don't know about a possibility to have the Fujitsu compiler suite on this machine. I think there will be, but I'm not 100% sure.
Yeah, probably it is quite important to enable the scalable vector extension. So I don't know if it is available, it could be nice.
And do you have already the date for the starting of this machine?
Somewhere in 21. I think it's beginning of 21, so I would say second trimester of 21, but I need to verify this information.
Thank you.
Okay, so and one more information, because there was a lot of discussion regarding OpenMP. So in case you don't already know, because I made a lot of communication on that, we will have OpenMP webinars starting in January 2021. And we will have, I think it's 5 webinar programs so far until May 2021. So 1 webinar per month. And we will have a small hands-on session at each webinar, but in the form of homework, because we only have 1 hour and a half, and all the talks will be given by Michael Clem from OpenMP and Christian Terboven from RTWH. So please join to the webinar if you have if you are interested in, because it's really OpenMP oriented for GPU programming. So I think it's going to be very interesting, and I hope we will have a talk in maybe June 21 on OpenMP roadmap. It would be nice. Yes, Simpa, please go ahead.
Well, here's topic for discussion. Thomas was using widely open ACC, and then we might be moving away from NVIDIA's dominance in the GPU race. AMD and Intel is coming. I'm not familiar. Is there a free version or AMD's version of OpenACC existing, or is that just called OpenMP? Anyone knows?
AMD support various different programming models. Their native one is HIP, and there's the CUDA to HIP migration path is somehow trivial, people say. But then there's also, I would say, a recommendation to try and use something which is independent of the vendor. And COCOS, of course, will have this. I don't know whether it already does have it. There is an implementation of SYCL or backend for SYCL, which compiles down to AMD GPUs. Anything based on OpenCL can, let's say, can essentially natively work very well on AMD GPUs and always has been able to. And so, for example, I think there's a HIP backend for SYCL, and there's also an OpenCL backend for SYCL. So those would be 2 ways of targeting AMD GPUs. But there's also, I think, a COCOS backend, or there will somehow, there's certainly efforts in COCOS to support this. It's needed for the US DOE program because they will have an AMD GPU machine as well. In Europe, of course, the Finnish machine is the one that's on everybody's radar. Lumi will be an AMD-powered GPU machine coming online next year. You probably know more than I do.
Yeah, I mean, that is sort of part of the lure of OpenMP to well, at least if you ask Lumi people, they will be they are promising that by the time Lumi opens, there will be a proper OpenMP support from AMD. Let's see if this comes true.
It's somehow necessary because of the DOE, in that the DOE have various contracts in place to guarantee this with vendors, and the timelines that the US DOE are requiring necessitate that these things will be available sometime in the next, I guess, 1 year from now. And so this should appear, I mean, of course, these will be available also, and these will be publicly available software when they come out. And so we have some hope that these will be available also for European usage, even if the development is driven significantly in the US.
And what is the timeline of M100? I mean, do we already see the end of listing, and what is in the future of Eurofusion's HPC support? What I forgot the time. In the point that are we going to be? Do we expect to expand on NVIDIA side, or are we maybe also going to be spreading to AMD and who knows what ARM or Future or whatever still, or Intel, still quite exotic platforms?
Francois might want to say something, but I can. Currently, the foreseen end of the M100 and the A3 Skylake petition is end of 23. A process has been started by various expert groups to consider what the next step will be. These groups have given reports. The latest one was effectively, can we do something together with the Japanese in the same way we had Helios? The next steps will be to more precisely specify what architectures we want, what performance we're looking for, and then start the process of trying to find some place that will host what we want for a price that we're prepared to pay. This whole process should, if we're lucky, end up with a machine in place, I would say, in the middle of 23. So we have a 6-month overlap between the end of Marconi and the new machine. Of course, things can slip, and we have to see what happens. Right now, we are foreseeing something like a machine, a combined performance of 100 petaflops, with 50 coming from conventional, whatever that means, and 50 from unconventional, whatever that means. The current interpretation is conventional will be something like Intel or AMD, and the unconventional is likely to be GPU in some form or another, but none of that is really guaranteed. We still have some time, and there could be an evolution over the next year or two. I don't know if Francois or Richard or anybody else who's also involved in these discussions wants to add anything.
Well, this is just basically to say that what Dave has been saying is completely correct. We are in the process of looking at how and with what we will be replacing the existing resources that were mentioned. So we have the A3 partition that we call conventional. We have the GPU currently. We have to be careful about what we expect the market to support in the future. On the one hand side, on the other side, also look at what our community can integrate as an architecture. I mean, successfully integrate. We see that with GPU, we are facing some significant issues right now. I don't think it would be wise to leap over again to something that will represent serious difficulty for our community for the next couple of years to come again. So we need to, I think, strike a right balance there as to be able to use what is conceived to be, I will say, conventional. This is to say for us, where we can maximize the use of the performance. That would be on the table. On the other side, keep an open eye and open technical possibility towards emerging systems that appear to be promising. So we need to strike the right balance there. That's always the game to play. And the idea of going with Japan was also to look into a possibility of reaching out to something that we don't have or we may not have in the EU, but for which access to will be significantly interesting. And this appears now to not be a possibility. So we have to look at what we can do within our own perimeter of action. The timescale indicated by Dave is correct. So we will just be starting the process early in 2021 to establish a working group that will be looking into technical specifications, probably based on the survey that was conducted, I think something like 2 years ago, but I think it will have to be updated to some degree. The survey was aiming at understanding what are the expectations in terms of needs from our community, and also, of course, looking at what people would like to have as potential architectures. I think these two things have to go hand in hand. By the end of next year, what we expect to have is an understanding of which site within the EU Fusion Consortium could provide the expected resources that we are looking at. And then in the remainder of 2022 and also part of 2023, we'll be working on establishing the procurement process, the purchase and installation, testing, and then towards the middle of 2023, the release and opening to the community of users. So this is the process we have in mind right now.
So I also would like to comment on that. So what Richard says, of course, it's what has been discussed with the expert committee, and the timeline is exactly what I also agree on. But I'm still skeptical about the acceleration part. I think 50% would be too much. Why? At the moment, I don't see that Eurofusion is really willing to give us the funding that we can transform the software stack from CPU to GPU. I really see that we have now these advanced computing hubs coming up. There's a delay, there's a cut in funding and so on. And these are all not the signals we really need to have the manpower to do this transition. So either Eurofusion spends more money in personnel who can make this transition, or if not, then we should stick to more conventional hardware. Otherwise, I fear that we will have the situation which we have to face now with Marconi 100, that roughly 10% workload is only there per month, which is not sufficient. And when you think about flops and green flops, of course, the energy consumption per GPU flop is better. But if they are not used and if the machines are just idle, I mean, then this makes no sense, of course. So I'm skeptical. At the moment, it's quite difficult to see which software will give us the chance to write code which is portable and gives the same performance on many different GPUs from Intel, from ARM, from NVIDIA. And I think it might be good to be more conservative and just to wait. what will survive in the end and what will come. So having another generation of more conventional CPU, I think, would give us the time to really wait until the powder dust is gone of the battle and we see who survived.
Well, I think you're right, Roman. What is not, I would say, settled and carved and stone somewhere is the fact that we are going for 50-50%. That has been a working assumption based on the projected needs by the community. So the community was asked and they projected this, and at the time they were asked, there was very little, I would say, experience, which is hands-on experience with GPUs in the community. So people looking at the potential advantages and the promises that were made and are still being made by the vendors, and also what other communities claim they can get out of the GPU systems, they made the projection. So this was a working assumption. I think what we'll be doing, definitely that is required, would be to go back again and look at this as these assumptions and see what really makes sense to be done based on the observations that you mentioned, that, you know, with Marconi 100, we see a usage that is alarming. And I see no way we can go for 50-50 if there is no scheme in place to boost the adaptation of codes towards GPUs. And even if you had boosted this, I'm not sure that we will reach levels of usage that we see now for conventional architecture. So I'm sure that the working group in the end will make a recommendation for a system that has a lower proportion of the GPU, and maybe will be complemented by something else than GPU. I don't know. We have seen in the recent past that we were going through different phases of accelerated systems. So we may again go for something where we have a dual provision of accelerated resources. Everything is possible at this stage. I mean, I don't see anything frozen in that respect.
No. So I think we are both in line. It was just this figure 50-50. I think more realistic is something like 2/3, 1/3. 2/3 conventional, 1/3 accelerated. And I think then we have still both choices. People who want to port their code can do so. People who have ported already their code can use these GPU flops. And I think that would be a nice compromise. And another comment on the new technologies. I mean, what we see now with Fugaku is this very nice memory bandwidth of 1 teraflop per second. And I think that is really the key feature, because most of the codes we see so far are memory bound. And if we can relieve that by having a better memory, and in principle, I think there are no technical reasons to use such memory, which you have in Fugaku now and in the GPUs, also combine this with CPUs. And I think then we would make a big jump, and even going to more fancy CPUs with bigger vector registers and all that stuff. I mean, these are more or less just theoretical flops, which we cannot achieve with our codes. It's really the bottleneck to the memory at the moment.
Agreed. I mean, we have to see. These are part of the uncertainties you always have to deal with. You know, you can project, but you don't know really in the end how much of the anticipated values can be factually used. This is not clear to me always, so we have to see. I think there are more questions. The chairman or the chair lady or woman should continue.
As for the Fugaku machine, their memory size will be very problematic because they are on one node only 32 gigabytes, which is quite close to what we have in GPUs. And quite similar problem from the Toma reported will also happen in the Fugaku type machine, I guess. And it's currently also the case for us. So the memory size also quite important.
So I think Simpa and Thomas wanted to raise something. Please go ahead.
Thomas can go first if you want.
Okay. I wanted essentially to say very similar to what Roman said, which is about memory, and this ties back to the summary slide that Todo-san showed earlier. If we can identify for the workhorse, and if we look, for example, at the share of resources that are being used across European codes on, for example, the Marconi CPU machine, and we look at, for each of these codes, to see whether they are memory bound, which is probably the case for the majority of them, or whether some of them are really compute bound. This could give us some better idea as to what really matters, right? rather than, for example, looking at flops or looking at memory bandwidth. I suspect that most of the codes will be memory bound, but we probably there could be some survey, some analysis, at least very simply performed. Because it certainly seems that memory bandwidth is very often the dominant thing. Just to touch on the capacity of something like Fugaku, my suspicion is that with the lower flops than a GPU, the restrictive capacity on something like Fugaku is probably less problematic for us than it is on a GPU, but this would certainly be something that I would have to look at in order to try and work out what, if this would be a problem or not.
Thank you, Thomas. Simpa, you want to?
This is again a slight change of topic. Okay. ITER will come and they will have their IMES and do we know if we should be? I mean, do they have a strategy that we should mirror, or can we affect that ITER will be ready to run our codes in the format and in the level where that we get them finished by the time ITER really needs its online data analysis done?
Unless somebody else wants to jump in.
I think, Dave, you may. I mean, I would have done so, but you may.
ITER's strategy, as I understand it, is essentially the lower performance type codes can be expected to run on the ITER clusters, that the clusters are evolving. However, the current thinking at ITER is that the highest end codes will never run at ITER. So the XGC type codes or equivalent that require vast computing resources will run outside of ITER, and it'll be up to the domestic agencies or whatever to try and put together the resources for their people to run the codes. So it could be FOE in the case of Europe, or more probably it will come through Eurofusion in some form or another. The trade-offs involved, I would say low-level GPU usage can be expected to also be run at ITER. I think that for some codes, it makes sense to have 1 or 2 GPUs per node for some limited number of nodes. For instance, I think the locust code from UKEA is running at ITER. I'm not absolutely sure of that, but I think it is running. But if you are looking at the very big codes, ITER's at the moment doesn't see itself as a supercomputing center. It will have resources to run the intershot analysis, the planning a shot type codes, and we expect those to become more sophisticated and require more resources. But I don't think anybody's planning at the moment to run a full-scale gyrokinetic calculation for the full ITER pulse before a pulse runs. So the sorts of codes that ITER is really interested in are somewhat lower fidelity. The my guess is that the big resources will come from trying to understand what happened in a pulse, and that will be external to ITER. But things can change. The ITER full-scale DT pulses are not foreseen for another something like 14 years. And so who knows what will happen in that period of time. 2025, they will start with fairly limited pulses, or maybe it's 2026, but the full-scale, very interesting physics pulses can only be expected, I think, in 2035 roughly, and who knows how the computing landscape will have evolved on that time scale. I don't think anybody can pretend to make predictions now of what will happen in 15 years' time.
So maybe, Dave, you may comment also on the IMAS, because
Okay, IMAS is essentially a data exchange format. It shouldn't really affect a big supercomputing code. It will affect how you get your data in, and it might affect how, if you are running a workflow, how you communicate with other components of the workflow. But internally in the code, I don't see that the IDS, the interface data structures, will affect how you write your code. It's essentially an I/O interface.
Dirona, I'm sorry, we are running late. So I propose that we stop this Q&A session. And thank you very much for the exchange. And I invite Yagi-san to give the conclusion and close talk to conclude this webinar. So Yagi-san, you will be able to share your screen.
Okay. Can you see?
Yes, we see your screen.
Okay, so there are 4 speakers, and first speaker, Dr. Todo, he present comparison between JFRS1 and NIF supercomputers. And this is his summaries, shows summaries. So performance of MEGA is compared among JFRS1 plasma simulator. This is SX-Aurora in NEC machine, and Fugaku by Fujitsu, based on ARM architectures. And good performance of MEGA is demonstrated for both strong and weak scaling of plasma simulators. MEGA achieved 6.3 to 6.7% of the peak performance for 256 or 4096 VEs on plasma simulators. And also performance of MEGA on JFRS1 and Fugaku is 2.5% and 4.4% respectively. And you can see this the figures. So the plasma simulator, it's almost the good scaling. And Fugaku point is a little bit lower position. This is due to memory bandwidth, essentially. And JFRS1 and due to the little bit poor memory bandwidth, so this is performance is lower compared to plasma simulator and Fugaku. Okay, so I'll move to next speakers. Next speaker is Dr. Mokalski, and he talk about benchmarks and validation of Marconi 100 HPC systems. So this is his summaries. And he tried to benchmark, for example, stream benchmark on host GPU and also on GPUs. And CPU's case, 266 gigabyte per second, and the GPU case, 845 gigabyte per second. Also, he tried to test the DGMM benchmark on GPU machine, and the performance is 6.7 teraflops is obtained. And also compared to the MPI process internode, and almost 100% theoretical value is obtained. And also the stable real code performance is investigated. And this is pretty good. However, he discussed this in, the availability of GPU machine is not so good. Sometimes it's okay, but almost many GPU parts are idling in the stage. So anyway, we need to consider to use GPU machine efficiently. So this is maybe future work. And then Asahi-san, Dr. Asahi present accumulating knowledge for performance portable kinetic plasma simulation code with COCOS and directives such as OpenACC and OpenMPs. And they developed the mini apply code, and this is based on the four-dimensional Browser-Poisson equations. And using this code, the benchmark is performed. So this is just an example for COCOS version of Poisson solvers. And compared to performance against Skylake GPUs. So you can see the COCOS is better performance compared to OpenACC or OpenMP. But so far, this ARM CPU's performance is not so good. So maybe tuning is necessary for the ARM. And also, he compared to the Fugaku, it's flow. He say flow. This is based on ARM A64FX. This is Fujitsu's CPUs, and compared to TSUBASA 3 and JFRS1. And good performance portability, keeping readability and productivity with COCOS. However, maybe in Fugaku, still we need some tuning to use COCOS. Okay, and finally, Dr. Hayward Schneider present gyrokinetic particle in cell code ORV5 on GPU platform, such as Marconi 100, run and future plans. And this is his summaries. OR5 on GPUs, 42 GPU with OpenSCCs. And particle ribbon GPUs and rest of code on GPUs. And so already the published paper, detail is find these published papers. And memory capacity limiting factor on Marconi 100, this is still some issues. Set minimum parallelization and maximum problems. And strong scalability now often limited by field solvers. Mixing OpenACC plus OpenMP paths hours. Okay, I think that's all. Thank you.
So it's time to conclude this workshop. So thank you everyone for attending. A big thanks to all of our speakers. And okay, I stop the recording.